Okay guys, let's take a look at today's lesson. So what we're looking at today is the fact that functions can be written as infinite series. And so what does that mean? Well, let's look at this. So this is a function right here. And there is an infinite series, this particular one, that actually can represent this function with the interval of convergence right here. So why would we want to have a series represent a function? Well, it is not always possible for functions to work the way we want them to. For example, if I wanted to integrate some functions, it's impossible to do by hand. So what we need is a way to estimate difficult functions. And this one is a fairly difficult function. So we want a way to estimate it. The estimations, this type of technique we're using, power series, is very prevalent in the upper level maths for estimating things that are just really too difficult to do by hand. And we would rather work with a polynomial like this rather than some other unusual function. So that's where we get into what a power series. We're looking at power series. How do we know if it's a power series? Well, first of all, series means that we're adding. Okay, series means that all the terms are being added. That's one thing. A power series would have something in addition to the n. Now with the other series we've been studying, they just have like numbers, right? If we would go through this, plug in a 0, 1, 2, we would just get a list of, adding up a bunch of numbers. But for a power series, we have an additional variable x that's involved. And so that's why they're called power series. All right, so these three are a really big deal for us in calculus. Actually, BC students memorize these three series. Now, you don't have to memorize them. I will give them to you, but that's just something that the more you see it, the easier it's going to be next year. So these are pretty important series, the series for e to the x, cosine, and sine. Now, these are fairly complex functions, and being able to write them as a polynomial is a pretty powerful thing. Pretty nice for us to be able to write them as a polynomial. Alright, so let's jump into our examples for today. What we're going to be doing today is we're basically going to use this one. We don't use this particular one very much in calculus. We use it in a kind of a different context. But we're going to be using this one to write some series from functions, and then we're going to be using these to evaluate. And so let's go to our examples on the next page. So we're going to use that series. Let's go ahead and write it up here. We're using this series right here. And so that means 1 over 1 minus x is equal to this summation . And this is our interval of convergence, all x less than 1. Okay, that's what we're going to be using. And we want to use that to kind of force this into a series. This looks very close to the original, but I have different numbers here. And so there's a technique that I'm going to show you. I'm calling it U substitution. You're going to use a little bit of a different type of U substitution next year for calculus, but let's look at this. What I'm going to do is I really want this to look just like this. So I'm going to take this location, this x, and I'm going to make it a u. So I have 1 over 1 minus u. I'm going to make it a u. This looks like a big blank, like a holding spot. I'm going to put everything in there from this equation so that I get this exact format. Because to get the exact format, then I can use this series. And so we're going to set it equal to what we want to work with, which is this one right here. Now our job is to solve for u. So I'm going to cross multiply, and I'm going to get 3 minus 3u equals 2 minus x, and I'm going to solve for u. I want to know what u is, because that's what I'm going to conceptually put right here. So we move the u over, so I'm going to move the x, so x plus 3 minus 2. So basically u is going to be x plus 1 over 3. This is what u is going to be. So what that's telling us is that g of x is the same thing as f of x plus 1 over 3. That's the relationship that we have just developed. So therefore, g of x is going to be the same thing as f of x plus 1 over 3. What does that mean? Well, that means that I'm going to take this and I'm going to replace the x with this expression. Okay, so now I'm going to be able to write my series. Now it's going to be 3 over 2 minus x equals the sum from 0 to infinity of, now instead of an x, I'm going to put this, x plus 1 over 3 to the n. I'm just substituting for x, for x plus 1 over 3 is less than 1. Okay, so I found out what this needs to be in order for us to use this this series right here. All right, so we have that kind of set up. We want to know where it converges. So this what I'm going to do with this one. This should look a little familiar to you. We did this a few days ago. So we do -1 less than x plus 1 over 3 less than 1. I'm going to multiply both sides by 3. So I get -3 less than x plus 1 less than 3. Then I'm going to subtract 1 from both sides. So I get -4 less than x less than 2. This is my interval of convergence. Okay, so we just took care of that, interval convergence. And that's a really big deal. I'm going to show you on the graphing calculator why that's a big deal. What does it mean to be an interval convergence? Why do we care so much? I'm going to show you on the graphing calculator why this is very significant for us. What they want us to do is, on the graphing calculator, they want us to graph this function and the sixth partial sum of the power series that we just created, the sixth partial sum. So that's s of 6. Okay, so the sixth partial sum. Well, what does that mean? That means that I need the first 6 terms of my series. So I put a 0 in here. So basically, let's just write it out. It's from 0 to 5 of x plus 1 over 3 to the n. So 0 would be my first term, all the way to 5 would be my sixth term, and I'm going to just put in those numbers. So that would give me, I put a 0 in here, I get a 1. I put a 1 in here, I get x plus 1 over 3 to the first power. I put a 2 in here, I get x plus 1 over 3 to the second power. I put a 3 in here, I get x plus 1 over 3 to the third power. I think you're seeing the pattern. X plus 1 over 3 to the fourth power, and x plus 1 over 3 to the fifth power. Okay, so this is my sixth partial sum. This is it right here. This is my sixth partial sum of the power series. So what we're going to do is we're going to go to our calculator and we're going to enter this part right here, that part in our calculator, and we're going to compare it to the function. So what does this infinite series mean? It means that if I were to write down every single term all the way to infinity, which we know we could never get to, I would have an exact match for this function right here. They would look exactly the same. So when I don't use every single term to infinity, like here I just use the first 6 terms, I have an approximation that's only partially good. It is partially good. Let's see what that means by it's just good part of the time. All right, so let's go to our calculator. Okay, so let's pull the calculator up. I actually have already input those two things into the calculator just to save us a little bit of time. So we'll get this pulled up and then I'll show you. Okay, so we go to y equals and see how I have right here. Here's my function, 3 over 2 minus x. Remember how we get those fractions? We do alpha y equals inner, and that gives us the fraction bar. And then here is my series right here. So we move this. If we just keep looking, well, I guess it's kind of hard for you to see. The whole series is written in here. Okay. So if we go all the way to the end, see up to the third, to the fourth, to the fifth, the whole thing is written in there. And so what I'm going to do is I'm going to graph both of these little guys. So I'm going to go over here and highlight my equal sign on these two graphs. So I want to graph this one, and I want to graph that one. And let's see what our window is set at. -8 to 5. That should work. Alright, so let's graph it and see what's going on. So the blue one is my actual function. The red one is my power series. Now, remember back when we found the interval of convergence? Do you remember what that was? Remember, it was from -4. It was from -4 to 2. I want you to look at this right here, -4 to 2. Look how closely these match from -4 to 2. After 2, they're just too far away, and actually are kind of a little bit far away right here, but good enough. The estimate's good enough right in here. Notice how the red is basically, as I get closer to this middle part here, it looks exactly the same. And if I used another term, then these would get closer together and closer. The more terms I use, the closer this red one is going to mirror the blue one. So that's the significance of the interval of convergence. It basically is showing us where the function and its series, its partial sum of the series, are really close. Really, really close. Okay. So let's go back to our work. So here, use the fifth partial sum of the exponential series to approximate the value of e to the 1.5. All right, so what does that mean? Well, what that means is we're actually going to use the series for e to the x, and we're going to use the fifth partial sum, which means I need 5 terms from that series. So 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus 1, 2, 3, 4, I need one more, x to the 4th over 4 factorial. This is my fifth partial sum. Really, this is my fifth partial sum, s sub 5. Okay, so in order to evaluate this or estimate this, I would put in the 1.5 for x, that x is going to be 1.5, and I would go in here and I put a 1.5 here and a 1.5 here, 1.5 here, 1.5 here, and I'd work it out. Okay, that's what I physically would do. Now I'm going to show you a technique on the calculator that will make your life easier, that I suggest you do instead of going through and putting 1.5 everywhere. Okay, that's what I'd have to do. I have to enter all my calculator. Well, let's look at another option for us. Okay, let's go to our calculator. And let's go to a clear screen. Let's actually go back to our y equals. Notice how I have in y3, I've input e to the x, the first 5 terms, 1, 2, 3, 4, 5. It's right here in y3. That's what I suggest you do. Put the series in your grapher, and then we're going to do something kind of fun. We're going to go to a clear screen, and we're going to make the calculator do that, plugging in the 1.5 for us. Okay, we're going to make the calculator do it. Well, how do we do that? What we do is we press alpha trace, and see how we have all of our options over here? If you recall, the e to the x was in the third in y3, so I'm going to press 3. So I'm going to take that function, and I'm going to put inside of it, open parenthesis, put inside 1.5 close. What I'm telling is, okay, calculator, go grab the function y3, and everywhere there's an x, put in a 1.5. That's what we want it to do. And then we hit enter, and it does it for us. Okay, this is our answer. That was way better and easier, less room for error, if you do it that way rather than sticking in 1.5 every time. Because what if you have multiple problems to do with e to the x? You wouldn't want to enter it over and over again. You would just want to have it in there. So to answer our question back here, we would say that e to the 1.5 is approximately 4.398. And that's how we use these series to approximate particular values of e to the x values, so e to the 1.5. Here we have this one where we want to use the fifth partial sum of the power series for cosine. Now if you recall from the other page, cosine is approximately, we're going to use the first 5 terms, and so this is the fifth partial sum. The fifth partial sum is actually, so 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial. There's a couple things I hope you notice about this. Notice how all the powers are even. And this is cosine. Of course, cosine gets to even things. Mean old cosine. Poor little sine. He gets to even things. He gets to alternate plus. So notice it's positive, negative, and so forth. So keep that in mind. You may need more terms, and I'm sure you'll be able to follow the pattern. So they want us to find cosine of pi over 7 using the fifth partial sum. So we would plug in pi over 7 everywhere there's an x, and so forth. Okay? But I'm going to show you how we would do it on a calculator. So we would say is approximately, now let's go to the value. So let me get some room in here. So let's go to our calculator. So we look at the y equals. Notice that I have cosine keyed in right here. This is the fifth partial sum for cosine. 1, 2, 3, 4, 5. I have 5 terms. Fifth partial sum. And this is under y4. So let's go second quit. Let's go to a clear screen. Now this time, what I'm wanting to do is I'm wanting to use the fourth, y4, right? We want to use that one to get to our estimate. So to pull that down, we go alpha trace equals, oops, I don't want y1, let's get rid of that one. So alpha trace, we want this one, we want y4. So I'm going to use 4 of, and we're going to do our fraction bar, which is alpha y equals, enter. Fraction bar, I love the fraction bar. And it's pi over 7, so pi over 7. So we're finding our approximation of cosine at pi over 7 using the fifth partial sum, and I get 0.901. So back to our problem. Okay, we would say that this is our fifth partial sum. So cosine is approximately, and the fifth partial sum was 0.901. All right, and so in this we've learned how to use those series to estimate values of those particular series for e and cosine and sine. And we also have learned to write our own power series and find the interval of convergence to determine how to do that. How do we work that? All right.